Everyone, thanks for attending this AJS session. So today with us we have Valentin Nkana. I guess most of you know him. He will present his most recent work on hybrid reduced order model for segregated with structure interaction solvers, an LAL approach at high Reynolds numbers. This is joined with Giovanni Stabile, Andrea Mola, and Professor Gianluigi Rozza. So the floor is all yours.
Good. Thank you, Mark. Thank you, everybody. We'll join the seminar. So before start, I wanted to to motivate you a little bit about what I'm doing. So to do that, I would like you to to have a glance of this current video. Let's say if you can see, basically this is the flow passing a airfoil that is moving up and down and rotating. So this is the form. So I want to build the entire reduced model on this system. So basically the forces applying behind, all the quantity of interest behind means the velocity, the pressure, the point displacement, and since we are in turbulent regime, the eddy viscosity. So this work was, let's say, is the second part of my project in my PhD. And it was a little bit of continuation of the first one that I did, which was not in turbulence, but in laminar regime. So, and let's say the main difference is that here we added some machine learning, capability to be able to, to predict what we call the eddy viscosity for, to build the entire reduced order model. So, the structure of the talk is the following. So I will give first, some motivation and application of my project. Then I will, show how, we move from experiment to simulation. I will show some, the driving equation behind two-shot interaction problem. I will give, I will recall the reduced order model in Notion. Then I will talk about, some experiment and result. And then to conclude, I will talk about how we have to move from projection to interpolation, because for now, projection is still too much expensive, even if at the end we still have, the result that we need. Then we have some references. So, as you know that today, CFD has been already an initial tool to the analysis and the design of many aerospace vehicles. Today, CFD can predict aircraft aerodynamic in cruises and complement what we call the wind tunnel and flight test in the aircraft design process. With this advancement in CFD, the number of wings that we use to test has decreased by a order of magnitude during the late 4 decades. It's a common, practice in CFD to analyze what we call the fashion-specific model. So here are some applications of FSI in real life, but the main application of my project are the A and the C, which is the aerodynamic floater and the bridge design in civil engineering. But we also have an application on cardiovascular and also in turbine design, mainly sometimes what we call, the rotors. So from experiment to, to simulation. You know that in the past, researchers used to, to use what we call the wind tunnel to be able to do some kind of experiment on the, on the flow passing an aircraft. But wind tunnel, to put all the ingredients to, to have, this, the setup of the wind tunnel is not easy. So with the advances in computer, people can easily have a computer, it's easy for you to do simulation. And this digital replica that we call here is today, a great tool, because we can build on that to be able, to construct what we call digital twin for many purposes. So here are the, I will show now, the driving equation behind the free structure interaction problem. So we assume that the flow is, we assume that the flow is incompressible. So equation 1 let's say, assume the incompressibility of the velocity. So equation 2 is the linear momentum, equation. And those who are familiar with Navier-Stokes can see that we have already an additional term that is appearing on the linear momentum, which say that, let's say, the mesh is moving, so the grid, you have, let's say, the grid motion. And since we are dealing with this, with the mesh motion, there's a third condition, which is called the space conservation law. Basically, we say that, let's say, the rate of change between one cell in two different frames is equal to the grid velocity at the interface. Let me say some magnitude. And omega here is a given cell in the mesh. And on top of that, we have initial and boundary condition to, let's say, to close the problem. And you can notice here, the time derivative is given in early form. So it's different. So it's not the standard one. So we are dealing with turbulence, with turbulence flow. So we need a way to, let's say, to resolve what we call, let's say, the eddies or the current, let's say, structure. So you can say that, okay, I don't want to do any, I don't want to resolve anything. So you can do what we call the dynamical simulation, which is so much expensive. And in this case, the real number is really low. So not too much behind. Or you can say, okay, I want to do the Reynolds average Navier-Stokes equation. You can also do what we call the large eddy simulation, and you can also do what we call, let's say, the detached eddy simulation. But in the literature, you can find another set of, let's say, methodology to be able, let's say, to do the turbulent modeling. So in this work, I use the Reynolds average Navier-Stokes equation, and you can see that equation 6 is the, let's say, it's same like the linear momentum, but you can notice an additional term that's appearing here that we call generally, let's say, the Reynolds stress. And equation 7 is what we call, let's say, the Reynolds average decomposition. And we have also another stress that is appearing, that is the viscous stress, which is, let's say, the viscosity of the fluid that we are dealing with. So now that, let's say, we have, let's say, the appearing of the Reynolds stress, we need a way, let's say, to model it. And we model it using the, what we call the Boussinet hypothesis, given by equation 8. So by combining, let's say, the Boussinet approach, by plugging the equation 8 in the equation that, let's say, we saw in the previous slide, we obtain equation 10. And in equation 10, you can see that, let's say, we have, let's say, the turbulent viscosity that is appearing, and also with, let's say, the gradient of the kinetic energy. And let's say the physical viscosity and the turbulent viscosity are called, let's say, the effective viscosity. And we also have, let's say, this number stresses that is arising from the Boussinet hypothesis. So now the point is to compute, let's say, this turbulence, let's say, viscosity. So both offline and online. So what about now the structure of, let's say, the modeling of the structure? So here we have a 2 degree of freedom that, let's say, we are interested in, which is what we call, let's say, the plunge, and let's say the pitch. So the pitch is the, let's say the motion responsible of the, let's say, of the top of the airfoil, and the plunge is the one that is responsible for the, let's say, the translation of the airfoil. So equation 11 and equation 12 are the main equation which drive the motion of the structure. But we have, let's say, the motion of the flow, we have the motion of the structure. How do we now combine them? So we combine them by equation 13. We see that, let's say, the flow velocity at the, let's say, in the y direction is equal to the grid velocity in the y direction, and this is equal to the velocity of the plunge. And together with that, we have also what we call, let's say, the balance at the interface, the balance of the forces at the interface. And here, let's say rho F is just, let's say, the stress. Let's say, I think it's the Cauchy tensor of the fluid. So having all that, we have all the modeling, let's say, of the fluid structure interaction problem. So now, just for the sake of completeness, for those who are familiar with, let's say, regional model, I will try, let's say, to give it, let's say, some motivation behind the scene. So why do you have to bother about with ROMs? So as you know that, let's say, traditional FS and traditional simulation that we call generally high fidelity are computational expensive. Most of the time, when you are facing the design of a new aircraft, you have to take into account a lot of parameters. For example, let's say the aircraft configuration, the mass of the aircraft, and some maneuvers. So if you want to do simulation for each type of parameter, you will end up with 1,000 of simulation. And in the industry, this is too much computational expensive. Let's say even money. So here now come to play now reduced order models. Reduced order model is let's say it's a kind of simplified version of the high fidelity problem, and it's able to accelerate, let's say, the solution of a given unsteady problem. And today, ROM is is the most important mathematical technique in the development of digital twin. So today, I don't think that, let's say, you can circumvent reduced order model anymore. So reduced order model can be used, to build reduced order model. In this case, I use what we call, let's say, proper orthogonal decomposition. Why? Because we are dealing with, let's say, the flow, and let's say we are interested on the, let's say, on the feature of the flow. Basically, because ROM give you, POD give you, let's say, is able, let's say, to, let's say, given a set of data, you can generate dominant pattern. You can obtain dominant pattern, let's say, based on those data. And from engineers, this is kind of important to know that. So we assume first what we call separability, given by equation 15. We see that given any flow or any field, you can decompose it as, let's say, weight depending of time, or maybe it might be a parameter, and also a let's say a basis depending of the space. So when you do, let's say, the separability, now how do we compute, let's say, the basis? So the field, let's say, the mode here. How do you compute, let's say, the mode? You can compute the mode in various ways, but here we can compute the mode with what we call the method of snapshot. Basically, it's saying that give me some set of data, I can compute, let's say, the transpose, and the transpose with, let's say, the matrix transpose of S and ST and S. And ST here is those collection of snapshot. And when you have that, you can be able to obtain eigenvalues and eigenvector. And the eigenvalue are the one that will tell you which data you have to take in account. So periodic Galerkin projection. So for the periodic Galerkin projection, in this case, we assume that, let's say, we have, given a PDE, equation 17 says that everything is discretized, both velocity and pressure. So we have the linear system, which carry, let's say, the velocity, and we also have the second linear system, which carry, let's say, the pressure unknown. So as you can see that the linear system on U is really high dimensional. So it lives in the high dimensional space. And also the linear system of the masses of the linear system of the pressure. And the LH here is the number of degrees of freedom in the mesh. So for example, here in finite volume is the number of cells present in the mesh. So now we end up with this equation 18 after doing the Galerkin projection. And the phi here is the matrix which carry all the spatial mode of the velocity. And the C here is the matrix which carry, let's say, all the spatial mode of the pressure. So when we do the Galerkin projection, we end up with a reduced system. So now the only, let's say, work here is to solve, let's say, the system and obtain, let's say, the coefficient at the online level. So these were done for the velocity and the pressure because we have let's say all the equation let's say driving the velocity and the pressure, but we don't have let's say we have an equation also for the point displacement, but we don't want to use a Galerkin projection on those, let's say, on the equation driving the point displacement. Why? Because this is to make the ROM independent of the technique that you use to move the mesh. Because to move the mesh, you can use Laplacian, you can use what we call a radial basic function, you can use what we call split analogy. So if you rely on doing Galerkin projection on the point displacement, you will end up having a ROM that depends on the technique that you use at the offline level. So to do that, we use a kind of combination with POD and radial basic function. So radial basic function is a kind of, let me say, it's a kind of artificial neural network with 3 layers. And as you can see in this picture, it's a kind of simple, let's say, network, which allow you, let's say, to interpolate efficiently a given problem that you have. So we assume again here POD with equation 19. And now the POD radial basic function is given by equation 20. So we assume the Galerkin the decomposition here, and offline we build a map between what we call here, let me say the parameter responsible of the grid, of the motion of the grid, which here is 2 degrees of freedom. So here is the plunge, and here is the, let's say, the pinch. So we build offline, let's say, a map which can interpolate between, let's say, the coefficient coming from the Galerkin projection and the parameter responsible of the grid motion. So when we do that offline, we obtain what we call some kind of set of weight for, let's say, that can be useful for interpolation at the online level. So at the online now, what we are doing, remember that those, the mode are fixed, so we don't care about them. At the online, every C new, the C new here is the parameter that let's say we obtain online. So every time let's say we obtain a new parameter online, we are able, let's say, to calculate, let's say, the predicted coefficient with the radial basic function thanks to those weights that we obtain offline. So by doing that, we can able, let's say, to reconstruct every time, let's say, the grid of the mesh. So now here is what let's say I included, let's say, as new in this, let's say, in this project, because let's say the first 3 was already done on my first project. So now in this case, to interpolate what we call the eddy viscosity, basically I use 2 methodologies. I use POD-NN and POD-LSTM. But here I will just, let's say, talk about, let's say, the POD-LSTM. So with the POD-LSTM, again, we assume, let's say, POD decomposition. But the interesting thing is now we are mapping the previous coefficient with the next coefficient with the previous one. So I have the set of data that I obtained offline, sorry. And then from that, I am building a map that can learn, let's say, this dependency between a previous coefficient and the next one. And when you do that, and you will see when we let's say we reach the result part, that how you choose the initial condition here is really important. So now we are going to the numerical simulation. So this is more, let's say now, more practical. So here is the test case that I use. The picture A is, let's say, this 3D. Is the 3D wing, and picture B is this, let's say, the cross section. So we take the cross section of this 3D wing, and we added some, let's say some spring to be able, let's say, to make the mesh, let's say, going up and also to rotate. And you can see we have, let's say, here what we call the angle of attack when, let's say, the flow, when we have an incoming flow, and we have, let's say, I don't know if you're able to see, also the forces that is applying on the airfoil. And to just see, it just, let's say, the zoom mesh around, let's say, the airfoil. So here are some simulation settings that I use during the simulation. But here I will just stress on, for example, let's say, the skill at the offline level, can affect really the skill online. So you have to pay attention which type of scheme, let's say, you are using offline. So here we know that, let's say, since we are dealing with turbulence regime are characterized high momentum convection. And with that, we will use, let's say, gusts of wind for, in the convective scheme. And also the time that we use also depend also on the number, depend on the real number. And here the real number is 10 million. So the more high the real number, the less time step you will use. And this one take a lot of time to complete. So here are some, let's say, the quantity of interest that I said before. We have, let's say, the velocity. Column A is the velocity. Column B is the picture and the pressure. Column C is the eddy viscosity, and column D is the point displacement. And the first row is the flow down, solution coming from the flow down problem. The second row comes from the POD with neural network, and the third row comes from the POD with the LSTM. So here now I have some, let's say, some L2 error. When you vary the number of modes, you have to see how, let's say, the error also behaves. And you can see that, for example, here, the almost best result that we have when we vary, let's say, the mode is with 20 modes for the velocity, 3 modes for the pressure, and 15 modes for the eddy viscosity. And the more mode you use, the more accuracy you can get. But also here you have to pay attention, because if you increase too much number of modes, the computation time may be greater than the computation time of the form problem. So you have to deal, it depends what you're looking for, or accuracy or stability. So it depends. So here, this table requires also, let's say, the time that we have when you, let's say, compare with the time coming from the flow order problem. And you can see the more you reduce the number of modes, the more you can reduce the time. But in the POD LSTM, you can see that the time is more or less close to the form one. And this one can depend, and this one can be caused from the structure of the LSTM model itself. And table 3 show that let's say show the dominant mode of each quantity of interest. For example, in the velocity, you can see that maybe with 4 or 3, we can reconstruct everything. For the pressure, which you can say for the pressure is quite high, and this is because at the interface we have, let's say, we have high pressure since the mesh is moving. And this table shows that also with one mode we can reconstruct the eddy viscosity, and also with one mode you can reconstruct, let's say, the entire displacement of the grid. So we move here for for example, in this case, you can see that, let's say, reducing, let's say, the mesh motion computational is really something that is interesting. Thanks to POD Galerkin projection. So what I showed, let's say, before cannot, let's say, really assess the let's say, the accuracy of the ROM. You have to go further and see that, and check, for example, let's say, the motion, let's say the time series of each data, for example, let's say the pitch, the center of rotation, and also the center of the mass. Because all those data are, let's say, are random, and you have to make sure that at the end you capture the same, that those data are close to the one that you have from the source model. And this makes sense because, as you saw that, let's say, in the motion of the structure, there was the forces appearing, and the forces are computed with the velocity and the pressure. So if the velocity are not well, the velocity or the pressure are not well reconstructed, this will also affect the motion of the grid, and somehow you will lose a lot of the error will be big. And you can see that, let's say, everything almost here everything here are almost connected. So we have to be careful when we, let's say, consult, let's say, a ROM for example, for a incompressible flow. So here are the let's say the time series of the lift forces that we obtained through the entire simulation. And you can see also that the number of modes affect also the forces appearing on the system. And there's a trend that, we have some setup of accuracy, but it's not too bad. And for company engineers, those, they like for that. They have to be sure that, they say, at least at the local level, you can able to reconstruct everything almost accurately. So now machine learning for eddy viscosity. So here are some, let's say, here is the training process of the POD coefficient coming from the data of the eddy viscosity. So I took 4 domain, the first dominant temporal coefficient of the eddy viscosity. I trained them in red, and then I also try to predict them also offline. So the red one is the training, the blue one is the prediction. And picture A is the, let's say, is the losses of both the training and the validation. So offline, everything seems good, because for those who are just let's say using PyTorch, they will be happy with this kind of result. So we train the neural network, we train the LSM offline with Python to import, let's say, the weight model online, so in OpenFOAM or Ithaca, can say. But we can observe, for example, online, that although the ROM can, let's say, can predict, because picture B is, let's say, is the comparison between, let's say, the POD coefficient of the POD, the coefficient obtained from the Galerkin projection and the coefficient coming from the LSM prediction. We can see that, let's say, the ROM, the ROM, let's say, the ROM, the online coefficient reproduce, let's say, the dynamic behind the system, but not well, because behind we have a lot of oscillation. And in the previous slide, I will show you why we can, what are the reasons of those oscillations. Picture A is, let's say, is POD-NN. So picture B is POD with LSM. Picture A is POD-NN. In POD-NN, I just choose, let's say, to compare the first dominant mode, as you saw that one mode was enough to reconstruct everything. So I just compare the first dominant mode with the form. When I vary, for example, the number of modes of the velocity and the pressure. Let's say In the LSTM, let's say I assume data dependence. So this depends on data. Picture A is that there's a map between, let's say, the temporal coefficient coming from the velocity and the temporal coefficient coming from the eddy viscosity. Thanks to this, to the Bosniak hypothesis, say that, let's say, there's a relationship between the eddy viscosity and the velocity. So picture A is purely N and picture B is purely LSTM. So when I saw this, I was asking myself what was wrong. Because first of all, I started to use, let's say, the normal LSTM. But by trying, let's say, to improve the result, instead of the LSTM, I used the LSTM encoder decoder. But it didn't change anything at the end. So I asked myself, what can be the reason of this kind of result? So in the literature, you can have various, let's say, explanations. And the first one is what we call the Lyapunov exponent, why those kind of oscillation may happen. And because the Lyapunov exponent tells us that the further in time you are going, because my simulation is transient, depending on time, so everything is unpredictable. So the further in time you are moving from the initial viscosity and the initial state, the more you can diverge between those two trajectories. And the second one is that maybe the number of modes, the number of snapshots that we use was not enough to reproduce, to cancel, let's say, those simulations. And also the sensitivity of the initial solution is also really important. That's why I said that how can we choose efficiently, let's say, the initial condition when you assume LSTM on the data. And also there's also one that we call the let me say the memory, because they assume that also given a set of data, memory can be present on those data. And if the memory is not present, you may also face this kind of oscillation. And to be sure that, for a deeper investigation, in the literature, there's one thing that we call the Ross exponent, which can tell you that given some data, memory exists or not. So now we talk about, let's say, Galerkin projection, everything is fine. But remember that we are projecting on the entire grid and it's expensive. So what I'm doing now, I'm trying, let's say, to project on a given, let's say, let me call it a sensor placement, as you can see here. So this is, let's say, it's a new test case that let's say I'm playing with. Is the flow passing the cylinder? So here, I don't want to project anymore in the entire grid. I want to choose some kind of, let's say, optimal sensor on the mesh, which can efficiently also reconstruct everything that I did with the Galerkin projection. So people call it DIME, but DIME generally take in account two. In DIME, you have to generate two modal space. But here you assume that, let's say, you assume one modal, let's say one modal space, and on those modal space, you have to construct, let me say, Lagrangian point for doing the interpolation. So, and this also has this, this application, this problem has also a lot of application in space recognition, and also in phase also reconstruction. And basically, the algorithm is kind of quite, let's say, flexible, and is more or less close to what we call, let's say, the Lagrangian interpolation in multiple dimensions. So here are some references that I use to, let's say, for this talk, but there are more. So if you have any question, I will try to answer as I can. Thank you for your attention. And that's it for me.
for the nice presentation. So if you have any question, feel free to ask also from the online audience as well.
Yeah.
Yeah, sorry, I was late, so maybe I missed this, but I was curious to know that you considered the viscosity which was an effective viscosity,
Yeah.
like viscosity plus viscosity with index T. I was curious to know that you have this effective viscosity because your problem is time dependent or because of turbulence.
Because of turbulence.
So
Turbulence.
so in case like if we have almost zero turbulence, you can consider viscosity as constant, or
Let's say if, as I said, depend on what you are doing. This, I mean, depend on what you are doing. If you want, for example, to do what we call dynamical simulation, you don't care about eddy viscosity. So there's not this mu t. You don't have the physical viscosity mu. But if you want to resolve what we call the eddies, to resolve, let's say to model, let's say the eddy, I mean the eddies, because they say that let's say when you have turbulence, behind the turbulence you can model let's say the eddies of the on the flow. So to model that now you have to use or Reynolds average Navier-Stokes decomposition, or what we call large eddy simulation. So it depends. So the time that when you decide if you want to model, you will have let's say this mu t, so the turbulent viscosity. So it depends on the flow.
Our question is that can you ignore it if it is if you don't have turbulence, right? The answer is yes. Basically those Reynolds stresses terms are zero in the Reynolds equation, and so you don't need the turbulence model to solve it. You're basically solving then a laminar flow. So in the absence of turbulence, you are just solving the usual Reynolds equation without a turbulence model, and because Reynolds stresses will be zero if it is a laminar flow. So you couldn't need a turbulence model. Anyway, so I also had this curiosity. It's like for your training for the LSTM, and where you have this Newt prediction, I guess, Newt prediction. No, before this. Yes, exactly, this slide. So how did you obtain this Newt? Did you have DNS data for such a case, or?
Yeah,
But did you have the DNS data for the case?
It's not the DNS, it's data from, mu t was computed with Reynolds average decomposition.
Okay.
Let's say basically here, I compute it with k omega ST.
Okay, so you use a turbulence model to predict
Yeah.
to predict this
To generate the data.
To generate the data. Okay, that was my curiosity.
Okay.
And did you try using some other besides LSTM some other another technique, let's say transformers, for example? No. The answer is no.
No, because I was thinking that maybe transformer can improve. I don't know. Maybe transformer can improve. We will see. But according to what they say in the literature, it depends on the data. So depend on what, let's say, depend on many things. Depend on a lot of things that can cause, let's say, this fluctuation that I have in the result. So it depends. Maybe transformer can do the job. I don't know. I will see.
In your last example that you are using interpolation, yes, this picture. So basically, I see. So you won't be concerned with the whole grid setup. No. You're just a part of the grid that where the motion is, and you're changing the grid. That's where your area will be focused.
Yeah, as you can even see here, you consider, let's say, the place where let me say the sensors are placed are effective, because when, let's say, you have, let's say, the voltage shading, it's mostly appear after the cylinder. So you consider, let's say, this result kind of makes sense. And also there are also some kind of, let's say, interpolation point around the cylinder, which is also due to the.
It's a part of it.
Yeah, so it makes more sense.
And then for your interpolation technique also, you will have this equation where you have d omega dt plus ug, the conservation of.
Yeah, so I do everything. I project everything. So I do the same thing, but either to do the entire projection that is orthogonal, I will use what we call an oblique one. I mean, the oblique one that is not that depends on the set of points.
Right, that's all.
Thank you.
I have a curiosity. Did you try with time extrapolation
Yet.
your line path?
Not yet. Not yet. But I don't know if I mean I don't know, but yeah, I mean I don't know if from open form, when I say open form environment, it may work because everything is random. Maybe you can lose something. I don't know. But if you are, let's say, the reconstruction is always close to the, for the, let's say, for the high fidelity problem, I think that maybe the extrapolation may work. I don't know. But last time, if I remember well, I was discussing when I was in this wide mall. So the guy said that the extrapolation, I mean, at the end of the day, you just have garbage if you do it, if you try it. So I don't know. Maybe it may work. I don't know.
No, because maybe the LSTM can work well also in time extrapolation. So it would be nice.
I hope that because offline you don't have any problem. Offline for sure you work, but online now I don't know. Online I don't know. But I mean the overall idea was just to to build a registrar. So let's say machine learning is not my focus. So I'm not using it, but I can still play with that to see what can help. So, yeah.
Okay.
There's nobody online.
Okay, there were people connected before. But, does anyone else have any question? If not, I guess we can. Oh, there's no question.
First of all, thanks for the interesting talk. I would like because you show that you consider it pretty high Reynolds number, like 10 million, I think. So is it still okay using compressible hair at this number?
I mean, if you want to be honest, even let's say this simulation is, it's not realistic because the flow over the wing, the air is compressible. So the air is compressible, so I don't know. So I mean, maybe I can try something now really realistic because if I just move from incompressible to compressible, I will have, let's say, almost the simulation will be close to the real problem. Because as you see, the relevant is high, and the velocity also is really high. And this velocity, as they say in the literature, is the minimum velocity that you can have in the real life. And also the viscosity also is also the viscosity of the air. So the only problem here is that it's incompressible. If we move to compressible, let's say we are, let's say we are sure that, let's say we do a simulation is really close to a real life problem. But at the end of the day, I think that for the compressible case, everything will be easy because the compressible case gives you already an equation for the pressure. Here we don't have an equation for the pressure, and it's kind of difficult, let's say to reconstruct almost everything because the pressure depends on the velocity. Here, with this let's say what we call, let's say, Poisson pressure equation. So yeah. So, but with the compressible case, I think that it might be more flexible to, let's say, to obtain something, let's say, meaningless. So yeah.
I think it's all from the audience. So thanks again, Valentin, for the nice talk.
Stop sharing.
Yeah, you can stop sharing and close the session.
Yep.